Is a scan of a bronze disc that has been generously shared with me by one of the museums attached to the University of Michigan. And so right now, it doesn't look like there's too many things wrong with it if you just visually look at it, right? You might have a couple of holes here, right, that we can visually see just because we can see that those areas are not blue. But if I turn on my bad edges, right, we can see that there are a lot of spaces around this disc that are not quite touching, right? We've got a lot of holes in here, a lot of really small things that we need to remedy, right? And if I go over to my part fixing info tool page down here, right, you can see we've got over 3,000 bad edges or bad contours, right? 73 specific ones that are almost touching, but not quite, that don't align. And then we've got almost 3,000 holes on this, right? This isn't something that I would expect anyone to go through and manually fix every last one of those holes on this STL. And then another issue, right, with this part is that if you're going to be using this or printing this off, you probably want to try and capture the actual like curves and like of the object, right? And this piece of scan data is really kind of chunky, right? Kind of blocky looking when we look at this. So I'm going to zoom out. Let's take a top view here. And first off, I'm going to just patch up some of these holes and near bad edges using the stitching tools. So that'll go through and kind of bring some of those edges back together so that they are properly touching. And then I'm going to patch up some of these holes, right? Depending on which technology we're using, right? Near bad edges can cause toolpath issues. Same with holes, right? You don't want to have gaps in the part that you're working with. Now we've got some issues that we continue to see with this part. But what we're going to do here is I'm going to use this noise shell fixing to clean up some of those pieces of floating geometry. So noise shells are like maybe little bits of triangles from that scan data that have been kind of like floating in space, not connected to the full model, right? So now I have this. It's in pretty decent shape. I've got some geometry that's overlapping with itself. But what I can do to try and help with that is use this smoothing operation. What the smoothing operation should do is kind of average out the angle between all of these triangles that are used to make this STL up. And then that should get me back to a bit more of that organic geometry that we'll see here. It should help average out this kind of stair stepping we see on the edge of the disc. And it should help kind of untangle some of these triangles from each other. So before I go through and fix any intersecting triangles, I'm going to try smoothing this out to see if that helps. All right. So now this looks a little, I know I don't have a reference picture, but this does look a lot more like our disc that we have at the museum. And you may have noticed down here in the bottom, I went from several thousand intersecting triangles down to about 400. So that's something that I can go through and maybe 4 more holes. So let's patch those holes up. Deal with some of those shells. And then clean up my intersecting triangles. And we have a solid part here. Normals are all good, so we shouldn't have any toolpath errors from the tool reversing on itself. Everything's connected. We have one solid shell here, so we shouldn't have anything that is kind of loose and floating, right? And then I could kind of move on, send this over to slice or set it up with supports and send that slice stack over to the printer, right? Next one I want to talk about is another piece of scan data, right? This is a dental scan taken from a set of a lower jaw, right? Now, typically for a part like this, you'd want to have a base so that you could, set it down on the table, right? But as you can see, there is no bottom or base. This part is just a singular surface. So we have a function that we can use on this to make it solid, which is called surface to solid. And what I can do is I can just set it up as block based, give it a Z height of, let's say 5 millimeters for now. I'm not going to hollow this out. So we're just going to drop it down 5 from the lowest point. But you'll notice that this is a little jagged, right? This isn't the neatest print that we could do, and we get a little bit of artifacting here as it tries to patch up the hole. So we can do better than this. So I'm going to just press Control-Z to undo, and then I can use a couple of the tools here in my editing suite as well as my fixing in order to get this to be cleaner. First thing I'm going to do is I'm going to use my multi-section tool to just kind of set up a straight cut on this to get rid of a lot of this bad contour, right? So I'm going to lose a little bit of the gums here, but the important information on this part really is the gums, right? It's the teeth. So I'm going to set a cut probably a little bit below tooth. I can use indicate to just kind of click on my STL and set my line. I'm okay with it being right about there. And then if I go into edit, I can use my section cut tool. Just go through and cut this. It's going to give me a warning. Hey, we got bad edges. This could cause issues. I'm okay with this. And now I have two parts. One is the area of the scan that I want to get rid of. And so I can just go through and unload that. And then I have the remainder of the scan that I can keep working with, right? So if I want to clean these edges up, I've got a couple of options, right? I can try to patch some of this up by using my hole fixing tools to create some triangles, like add boundaries here. So I can go here and then just add some information there. And then use my freeform hole filling tool to just fill that up. Smooth that over. I can do the same thing over here. And then for some of this area over here, right towards the back, I might want to just trim it. So what I can do is I can use my triangle marking tools in this ribbon, give it a polygon selection, tell it to remesh so that I'm able to just kind of cut exactly the triangles I want off. And then take a view from the top and just line this up so that I'm able to trim my STL. I got to close the polygon here. And that's going to mark all those triangles, and I can just delete those. And that cleans up my edge. I'm going to need to go back and take care of these polygons there, right? But I can continue this process of just cleaning this up, getting rid of information that we don't necessarily need in the final print. Delete that, and go through and clean this up, right? So I'm just going to go through and finish that process up here. Where I just continue to remesh this part, clean that up. If I were to try and print this part right without giving it a base, I would end up with just a, if the slicer were even to parse it at all, right, I would end up with, say, if I was making this in a stereolithography process, that didn't work. If I was making this in a stereolithography process, I would end up with possibly just a film, right? Best case scenario, I'd end up with a film floating in my resin bath. And that would be a mess to clean up. That wouldn't be a usable part. It's probably similar with DLP, right? Or for metal, I would just end up with a very thin, right, surface of metal here. Well, most likely the slicer would not be able to parse this part, right? Or it would say, hey, there's not enough information to slice this. So we've got this one surface that's still a little jagged, but I can go through and I'm just going to clean up my noise shells. That should get rid of my floating little islands of geometry. And then I will go ahead and, in the interest of time, just hop over into surface to solid, go over to block based, set a height, let's give it 7. And that will go through and create the base for us so that we can go send this over to the printer. I'm not too worried about these intersecting triangles, but I can clean them up. Intersecting triangles can cause situations where you have overcure on a part that is printed in stereolithography process. So you might have discoloration, or in a situation for like laser powder bed, you might end up with different mechanical properties there. If laser powder bed for plastic, you would probably end up with some discoloration in that region as well. All right. Or something might even break because there's been too much, energy put into it. Okay, so those are kind of the first 2 files, right? I was able to fix those pretty quickly. And the last one is this model that I have of a truck. So this is when I import it, what this looks like. There's a lot wrong with this model here. Generally, the first step to any fixing, right, I recommend is visually inspect the model, right, get an idea of what's going on. So I can use some tools over here with my sectioning to take a quick cross section, right? I've got all of my seats on the inside. I've got my steering column. I've got the dashboard. I have a whole bunch of little holes for individual LEDs that are going on here. I don't need all this information, right? When I print this, I just need the outer shell for this part. There's a lot of steps that I needed to go through and fix this. Generally, places I would start, right, are fixing these inverted normals. So the inverted normals are marked by these surfaces that are in orange. What this can cause in the slicing process, right, is a confusion in your toolpath. For SLA processes, it might error out the slicer. For DLP processes where you need to have solid blocks of information, it might cause closed shapes or areas that are supposed to be closed to be open, and then you'll just be missing large pieces of geometry or have a hole in your part and then fail the print, right? So one of the things I would want to do here is go through and invert these normals first, or fix these inverted normals. That gets through most of my outer part here. You'll notice that the grill is showing up as has been inverted back to be inside out. I can fix that myself just by marking this. Oh, sorry, I need to use this tool. And then just by marking this shell, grabbing background, and then manually telling it, hey, flip that back. I realize I'm using kind of a greenish color here. Let's make this a little bit more gray so that the marked triangles show up a bit better, right? So that's step 1. Step 2 would probably be going through and trying to close up a lot of these bad edges, right? If the triangles don't meet, then we might not have cohesive scan paths or tool paths for our slice files, which could cause failure at the print or just failure at the slicer itself. So the next thing I would recommend doing, right, I know that all these inverted normals here are from this grill that I inverted myself, so I'm not worried about this number in the diagnostics page. But what I would want to do here is stitch this together and try and clean up a lot of those bad edges. You see that took care of a lot of the issues that I was seeing through these yellow lines, right? From here, what I would probably want to do is go through and simplify the geometry, right? I don't need all the internals to this part. That's going to add material. That's going to add time, build time. These are things that we don't need to keep, right? Unless we're planning on maybe printing this in some kind of transparent material. I can kind of declutter my view by turning on this hidden line function. And that will hide a lot of those yellow lines that we're seeing that are defining the rest of the vehicle. while I'm trying to hide it, right? I don't need this interior to the trunk. I don't need all of these lights back here, right? Somebody went through and actually designed this very in detail, right? Or had a lot of detail on this when they were designing it, creating the STL file, but I don't need all of that to print it. So what I can also go through and do here is I can start manually selecting which shells that I don't need, right? So this can be a little bit of a manual process sometimes, right? But it might be necessary in order to clean up the part. So I would go through, delete all these seats in here, get rid of the steering column. Another thing to think about while you are going through this process is what detail can I capture and do I need it, right? So if you look out here, we have the windshield wipers. I might not need to have this detail. It might actually make it more difficult for me to work with this, right? So I can go through and get rid of the windshield wipers as part of this process. Some other things to notice through the visual inspection here, while I'm here, is that I don't have an axle connecting these wheels. So what I might need to do later is go through and add a cylinder to go through and make sure that these are connected to the part, or find some way to join these to the rest of the part. I might drill a hole in the finished product, right, and then run a rod through it. If I wanted to do that, what I could do is just grab the editing tool, and then we'll see if this works for me well, is I can use the perforator, right? And I can set the radius of my rod. Let's say I've got a 2 millimeter diameter rod that I'm going to use, and then I can just X section. There we go. Go through and hide first wheel. Just line this up. There we go. Okay, looks like I need to fix this first. That's fine. So there is a longer process where I go through and clean out, right, this entire truck. Once you kind of get the feel for it, it does become a little repetitive. So I have, through the magic of television, right, a version of this part that I've gone through, cleaned up a lot of things. You notice that we still have a lot of internal geometry here. But what I'm going to do next is show you what is called the shrink wrapping tool that can help go through, and it's going to take and look at this part and create a cohesive outer surface for me. And then it's going to take care of all of that internal geometry and toss it out because I don't need it. So I'm going to go over to shrink wrap. I have two options here, global and local. Like if I wanted to just wrap the wheels, I could mark the wheels up and it would go through and take a look at just the wheels. But right now I'm going to use local. And so I'm setting a sample interval, a gap fill, and a little bit of extra thickness here to add a little bit more robustness to the part. So sample interval is how Magics is going to take a look at the part, kind of chop it up and read the geometry, right? A smaller sample interval is going to take a little bit longer to run, right? But it's going to allow you to save more detail in your part, right? Gap fill is going to tell Magics what size of a gap in your geometry or gap between surfaces it should go over, and just paste kind of wallpaper over. I set it kind of small here just to try and cover some of the gaps that we have between the doors and kind of the body panels. Adding extra thickness also helps with that process of just like giving it a little bit more robustness, especially in thin areas like we might have with the grill, right? Something to keep in mind while you're going through and running these fixing processes are, what are the physical limitations of my printer? What is the detail that I'm able to capture, right? And if you run into parts that have a smaller dimension to it than you can capture, you might want to either add some weight to it, either through something like the shrink wrap part or an offset operation, or get rid of that piece of geometry if it's not strictly necessary. to the part itself. If you want to kind of get a read right for what pieces of geometry might fall in that range, I have a few tools over on the right that can help measure that. I've got some distance measuring tools, radius, angle, right? You can do a thickness measurement. You'll notice I can interact with the software again, which means the calculation is done. And if I cut away here, this actually performed differently than it did the last time I ran this operation. Interesting. But we do have a much cleaner part here, right? You can probably go through and try and unify this body. And what this should do is that should also help clean up some of the insides here. All right. So clean up my noise shells. And then part of what I'll also need to do here, right, is go through and identify which shells are which, and then how to attach everything. Right. Most of these are going to be things like each wheel is its own shell, right? Need to make sure I have a way to run something through each of those and connect it to the car. So I could run a cylinder through here and run a Boolean operation to connect those to the rest of the body. And then I believe kind of the rest of my shells are smaller objects that are still in here that I might need to clean up manually. But given what I've shown here, I'm running low on time. You can kind of imagine what that process looks like, right? So I think this is when I should be handing it over for questions.
Thanks, Eric. Sorry, it took me a second to find myself here. That was amazing. I hadn't seen the shrink wrap feature, which I thought was really cool. So thanks for sharing that. We do have a few questions that came in while we were talking. In fact, the one question we got 2 different times was, how much does Magics cost? If you don't mind, I'll take that one, because Allegheny is the authorized education solutions partner for Materialise in our area. And the good news is Materialise Magics is not sold the way it used to be. It used to be a very expensive package. It's now sold as an annual license. And the price really depends on whether you just need a single seat or you need a multi-seat license. You need the seat to be static, or does it have to float in your campus or your lab? Do you need any additional advanced modules? So short answer is it depends on what the price is, but I'll tell you that a single seat for all the features that you just saw Eric demonstrating, you can get a single seat with the educational discount for under $5,000 a year. So it's much more affordable than some of you may have remembered what Magics used to cost. All right, a couple of more questions. Does Materialise Magics play nice with SolidWorks Autodesk files, or do we need to stick with pure STLs? Eric, do you want to answer that? Or Carlos?
Yeah, I can field that question.
Okay.
So out of the box, right, just a Magics license itself can handle STLs, 3MFs. It can handle step files, so you can import native CAD data and then run some fixing operations, or really more like process-based editing operations on it. So like if you need to resize holes so you can drill them out later because they're not printing well, that's something you can do to the CAD data before converting it to an STL so that you can slice it. We also recently gained the ability to handle end topology implicit files natively. And then if you need to handle a variety of CAD data like CATIA files and SolidWorks files and all of that in its original form, there is the import module that can be added on and allows you to import those.
So we can add an import module, and you can bring those files in directly from your CAD software.
Yep.
Got it. Okay, good. Any tips for teaching students how to spot the errors you showed on their own? So I guess that's asking, you were able to see those errors right away. Is there any way you can easily show somebody else how to do that?
So one of the things that's helpful is that part fixing info toolbox that was kind of in the bottom of the page, right? It helps flag some of the issues, but it's not going to catch everything, right? So I mean, step one, right, is to know what the part needs to look like and be able to spot missing geometry. So some of it is just a little bit of time, a little bit of practice, but I mean, the big yellow lines help, and the orange faces showing where the triangles are facing the wrong direction, that's gonna handle two of it. So anytime you're seeing red is generally or yellow is an indication that something's wrong with the part.
Okay, good. Autofix. You talked about autofix. Does autofix ever mess with the actual dimensions of a part?
It can. It's usually pretty subtle, but it's software. Sometimes things can go a little bit awry. I have a part that I could show where it will just like erase the small peg because it was missing the body of the peg in the STL. It just had one face, and then you lose that if you just go through auto fixing blind, right? So it's something that you do need to keep an eye out for, but as the software's gone through iterations, the fixing algorithm's gotten better and better and better.
We have one more question, unless anyone else has thrown one in. Well, we might have answered this already. Is the software license perpetual? So, as I mentioned at the beginning, it's an annual license. Carlos, you want to talk any more about licensing in general, how it works, multi-year or single year?
Yeah, I'll jump in real quick. So we, as Ned kind of detailed at the beginning, we have faded away from the model of selling perpetual licenses. All our software is now an annual license. And when you choose any type of software package or license or module, you do have the choice of selecting a static local license or a floating license. And the difference is the static local licenses are installed in one system, one computer. That's where the software lives, and that is the only place you can use the software. Now, the floating licenses, for those of you that might want to have access via network, via server, right? There could be a case where you need multiple people to access and log into the software from various locations. Then that's what you need. You need a floating license that gives you that access via your company server or your school server. So, but yeah, moving forward, only options we have are annual licenses, which give you access to always having the most updated version of Magics.
Great. Thanks for the explanation. That's all the questions we have, and we're right about the end of our time. So, Carlos and Eric, boy, I really appreciate you joining us today and getting so deep into something that I know a lot of people with advanced experience with 3D printing struggle with, which is trying to get their beautiful design out onto a 3D printed part. So thanks for taking the time to do that. By the way, anybody who registered for the webinar here today is going to get a recording of the webinar. And if you'd like more information, including pricing or specifications or what printers are we compatible with, etc., just reply back to the email that you get at the close of the webinar, and we'll be happy to answer any of your additional questions there. So thanks again to Carlos and Eric, and thanks to everybody who attended today.